Hello everyone, welcome back to this online class. Today we are going to look at how to solve systems of linear algebraic equations, and in particular we are going to look at the Gauss-Seidel iteration method. So we have this question. We are asked to perform 3 iterations for the Gauss-Seidel method to solve the system below. The starting initial guesses are that x1 at level 0 is 0, x2 at level 0 is 0, x3 at level 0 is 0. But let's see how to go about this problem. Remember, Gauss-Seidel iteration method will give you the approximate solution of x1, x2, and x3, but not the exact solution. But the solution will converge to the exact solution. So, there are 2 methods of going about this problem. The first method, call it method 1. In method 1, we are going to use matrix vector form. We write to use matrix vector form. So what it means, we are going to write our system in matrix vector form, and then we apply the alternative formula for the Gauss-Seidel method. So in matrix vector form, let's start by writing the coefficient matrix. That's 5, 2, 1, 1, 4, 2, 1, 2, 5. Matrix of coefficients, the unknowns are x1, x2, x3. The solution matrix or in general, A times X is equals to B. Remember, AX is equals to B, where A is the matrix of coefficients, X is the unknown column vector, and B is the solution matrix. Now, the coefficient matrix A can be decomposed into 3 components. So you write A is the same as L plus U. Let's start with D. Plus D plus U. We are partitioning A into 3 components. L is the lower triangular matrix. D is the diagonal matrix. U is the upper triangular matrix. So look at the leading diagonal of A. And so from that matrix A, you can now get L. We are only interested in the elements along or simply below the leading diagonal. The rest are 0, so we'll have 0, 0, 0, 1, 0, 0, 1, 2, 0. To get D, only the elements along the leading diagonal, the rest are zeros. And finally, to get U, we now need the elements above the leading diagonal. The rest are zeros. When you add all of them, you get the coefficient matrix A. So, having found L, D, and U, what is the Gauss-Seidel iterative formula? So you write Gauss-Seidel iterative formula is that x vector at level k plus 1 is equals to h times x vector at level k plus a constant column vector c, where this h is given by, so where h is equals to negative d plus l, or l plus d. Let me start with l plus d. L plus d inverse times u so that is our h. And then the other one, which is c, is given by, so let me get rid of this plus. Our c is equals to l plus d inverse times b. Remember, k ranges from 0. You can write for k is equals to 0, 1, 2, 3, etc., depending on the number of iterations that you need to perform. So now, back to our problem. We need to compute h and c. And once you have their values, we now go back to our iterative formula and perform 3 iterations. So let's start by finding L plus D, and then we get its inverse. So you can write here now, our L plus D, when you work it out, you need to get 5, 0, 0, 1, 4, 0, 1, 2, 5. We need the inverse, L plus D inverse. Of course, you know how to find the inverse of any square matrix. There are 3 methods. You could use matrix inversion method, which employs what you are calling the cofactor expansion. You could also use Cayley-Hamilton theorem or the Gauss-Jordan elimination method. Any of them will give you the correct answer. And so you need to get your answer as 0.2, 0, 0, negative 0.05, 0.25, 0, negative 0.02, negative 0.1, 0.2. That's the inverse. What else do we need? We have U and we have B. So let's now compute H and C. So therefore, our H will be equal to negative, and I'm using this formula. So negative of that inverse then times u. So we write that it will be negative of 0.200, negative 0.05, 0.250, 0.02, 0.1, 0.2. Multiply this by u. Our u is 0, 2, 1, 0, 0, 2, 0, 0, 0. When you work out row times columns, you need to get 0, negative 0.4, negative 0.2, 0, 0.1, negative 0.45, 0, 0.04, 0.22. That's our H. Let us find C. Our C is equals to, look at the definition, it is the inverse of L plus D, then times B. So I'll write the same inverse, 0.200, negative 0.05, 0.250, 0.02, negative 0.1, 0.2 times our B, which is equals to 12, 15, 20. When you work out this, you need to get C is equals to 2.4, 2.40, 3.15, 2.26. Now with H and C, we only need the initial guesses, and then we now perform our iterations, just 3 iterations. What are we given as the initial guesses? We are given the initial guesses that x1 at level 0 is 0, x2 at level 0 is 0, x3 at level 0 is 0. What does it mean? That the vector x at level 0 must be equal to the 0 vector with 3 elements. This, so that the first is x1 at level 0, the second element is x2 at level 0, and the third element is x3 at level 0. Now let's perform the first iteration. You write here first iteration. First iteration. Look at the iterative formula that x at level k plus 1 is equals to h at level k, h times x at level k plus c. So first iteration, you put k is equals to 0. Put k is equals to 0. We are going to get x at level 1 is equals to h times x at level 0 plus c. We have these vectors and matrices. You know h, you know x. Let me substitute. Our h, we got, can refer back here. This one, 0, negative 0.4, negative 0.2, 0.1, negative 0.45, and the other one is 0.04, 0.22. You need to multiply this by our x at level 0, that is 0, 0, 0, plus c, which you have found 2.40, 3.15, 2.26. When you work this out, you need to get your answer to be 2.40, 3.15, 2.26. What do you mean by those values that you have just it means that x1 at level 1 is equals to 2.40, x2 at level 1 is 3.15, and x3 at level 1 is 2.26. Go to the next iteration. Second iteration. Here you put k is equals to 1 in the iterative formula, so that we are going to get x vector at level 2 is equals to h times x vector at level 1 plus c. When you make the substitutions, you will have 0, negative 0.4, negative 0.2, 0, 0.1, negative 0.45, 0, 0.04, 0.22. X at level 1, 2.40, 3.15, 2.26, plus our C, 2.40, 3.15, 2.26. Let us work out what is rows, columns. Then you add. You need to get x at level 2 to be 0.688, 2.4480, 2.8832. What does it mean? That x1 at level 2 is 0.6880, x2 at level 2 is 2.4480, x3 at level 2 is 2.8882. And finally, the third iteration, third iteration. In this case, you put here is equals to 2 in the iterative formula, so that we'll get x vector at level 3 is equals to h times x vector at level 2 plus c. When you make the substitutions, you'll have 0, negative 0.4, negative 0.2, 0.1, negative 0.45, 0, 0.04, 0.22. That's our h. X at level 2, 0.688, 2.448, 2.8832. Our C is 2.40, 3.15, 2.26. You can multiply and then you add to get this column vector 0.8442, 2.0974, 2.9922. So this means that x1 at level 3 is 0.8442. X2 at level 3 is 2.0974, and X3 at level 3 is 2.9922. So this approximate equal to X1, X2, and this is X3. So we are only asked to perform 3 iterations, and that we have the approximate values of X1, X2, and X3. That is the first method when you use matrix vector form. Second method, method 2. Here, we don't need to write the system in matrix vector form. Let me explain what happens in this case. You're given the system of linear equations that 5x1 plus 2x2 plus x3 is equals to 12. X1 plus 4x2 plus 2x3 is equals to 15. X1 plus 2x2 plus 5x3 is equals to 20. So what happens here is that in the first equation, you need to make x1 the subject. So I'll take 2x2 and x3 to the right-hand side. So we'll have this that x1 is equals to, we are dividing by 5, 1 over 5 into negative 2x2 minus x3 plus 12 over 5. In the second equation, now x1 and 4x2 the subject, you now take this to the right hand side. Now, even before you work it out, in the first equation, on the left you put the level k plus 1. On the right you put level k. Here again level k. So why are we making x1 and x2 the subject in this case? I want the level of x1 in equation 2 to be k plus 1. And in equation, the level of x2 to again to be k plus 1 is only x3 that is k. So what we'll have is this, that I'll make x2 the subject, yes, but the x1 that will be on the right hand side will be at level k plus 1. So you even take this to the right hand side, only the level will change. So in equation 2, we will have x2 is equals to 1 over 4 negative x1 minus 2x3 plus 15 over 4. So that the level on the left is k plus 1. And you see already we know x1 at level k plus 1 from equation 1. So we use that value that we have found of x1. So the level of x1 must be k plus 1 because already we know it. I don't know x3, so let's use that as level k. And finally, equation 3, you now make x3 the subject, and now everything will be level k plus 1. So x3 is equals to 1 over 5 negative x1 minus 2x2 plus 20 over 5, which is 4. But now already we know x1 at level k plus 1 and x2 at level k plus 1. So we can use the immediate values we have found. So the level here is k plus 1 and even here it is k plus 1. Already they are known. So that you get x3 at level k plus 1. That is the iterative formula for k is equals to 0, 1, 2, 3, etc. And remember that x1 at level 0 is 0, x2 at level 0 is also 0, x3 at level 0 is also 0. So let's start performing the iterations. First iteration, in this case you put k is equals to 0. What are we going to get in equation 1? We are going to get x1 at level 1 is equals to 1 over 5 negative 2 x2 at level 0 minus x3 at level 0 plus 12 over 5, that is 1 over 5 negative 2 times 0 minus 0 plus 12 over 5 That will give you 2.40. Equation 2, x2 at level 1 is 1 over 4 negative x1 at level 1 minus 2 x3 at level 0. Remember k is 0. You are adding to 15 over 4. That is 1 over 4 negative 2.4 minus 2 times 0 plus 15 over 4. When you press that, you need to get the value of x2 at level 1 to be 3.15. Equation 3, x3 at level 1 is 1 over 5 negative x1 at level 1 minus 2x2 at level 1 plus 20 over 5, which is 4. And so, by substitute, I'm going to get 1 over 5 negative 2.4 minus 2 times 3.15 plus 4, that is 2.26. Second iteration, put k is equals to 1 in the negative formula. That will give us the first equation will now be x1 at level 2 is equals to 1 over 5 negative 2x2 at level 1 minus x3 at level 1. And that is 1 over 5 negative 2 3.15 minus 2.26. I have left out something. There's a plus 12 over 5. Let me insert it here. There's a plus 12 over 5. So you add this to 12 over 5. And so what do you get? X1 at level 2, 0.688, 0. Question 2, x2 at level 2, the 1 over 4, negative x1 at level 2, minus 2x3 at level 1, plus 15 over 4. Substitute, you get 1 over 4 negative 6, of course 0.688 minus 2x3 at level 2, that is 2.26 plus 15 over 4. When you press this in your calculator, you need to get the x2 at level 2 as 2.4480. X3 at level 2 is 1 over 5 negative x1 at level 2 minus 2x2 at level 2 plus 4, which is 1 over 5 negative 0.688 minus 2 times 2.448 plus 4, and that should give you 2.8832. Third iteration, here you put k is equals to 2 in the iterative formula, so that the first equation, x1 at level, now the level is 3, k plus 1, that will be 3. That is 1 over 5 negative 2x2 at level 2 minus x3 at level 2 plus 12 over 5 will give us 1 over 5 negative 2 times 2.448 minus 2.8832 plus 12 over 5. When you press that in your calculator, you need to get the value of x1 at level 3 to be 0.8442. 0.8442. Equation 2, x2 at level 3, that is 1 over 4 times negative x1 at level 3 minus 2x3 at level 2 plus 15 over 4, that is 1 over 4 times negative 0.8442 minus 2 times 2.8832. You're adding this to 15 over 4. When you press, you need to get 2.0974. Finally, the third equation, x3 at level 3 is equals to 1 over 5 times negative x1 at level 3 minus 2x2 at level 3. You're adding this to 4. Substitute, you get 1 over 5 negative 8, of course 0.8 442 minus 2x2 at level 3, that is 2.0974. You are adding this to 4. When you press this in your calculator, you need to get 2.9922. And therefore, because we are only asked to perform 3 iterations, it means this is the value of x1, approximate value. This is x2. This is x3. You can compare with the exact solution. Exact solution. Remember, for you to get the exact solution, you could use Cramer's rule or LU decomposition or the matrix inversion method. You need to get x1 is equals to 1, x2 will be equal to 2, x3 is equals to, look at the values we have found. X1 is 0.8, that's approaching 1. X2 is 2.09, which is approaching 2. And x3 is 2.99, that is very close to 3. That means if you had proceeded with maybe other iterations, we will have approached the exact solution. Or the solution is said to converge to the exact solution. So you realize that using Gauss-Seidel iteration method is more accurate than using Jacobi iteration method. So thank you all for watching this video. Please subscribe to my YouTube channel. That is Professor Francis Okech. When you go to the YouTube search, type Francis Okech or Prof. Francis Okech, and you will find me right there. Also, don't forget to comment, like, and share this video. When we meet next time, we look at more problems involving iterative methods of solving linear systems of algebraic equations. Bye-bye.